Hello and welcome back to Apt for You. In this particular video, we will be discussing a very classical problem from arrays and an important problem too. So basically the problem is about counting the inversions, right? So you can clearly see on your screen the problem I have basically picked up from Geek for Geeks, and it is counting inversion problem. Now what do we understand by inversion? So this is the technical definition that they have basically given. We will basically try to keep things as simple as possible. So let us understand through an example. Suppose I have an elements in an array like 2, 4, 1, 3, 5. This is the original array that is provided to us, right? Now, if this array would have been sorted, what should be the arrangement? The arrangement should be something like 1 followed by 2, followed by 3, followed by 4, followed by 5. So sorted in the sense sorted in ascending order, right? In the ascending order. So what is the pattern that you are observing? That the elements are basically increasing as we are moving towards the right. Okay, they are non-decreasing. Okay, so similarly, now if you focus on the original array, right, this is our expectation. If the array would have been sorted, this should be the arrangement. That is, the smaller if you consider any smaller element, if you consider any element, the elements to the left of it is smaller, the elements to the right of it is greater. This is the expectation. But if you focus on this array and focus on any one element, suppose 4, you will find that if there is any element towards the right of this 4, means from here till here, okay, you just look in the right. If there are any elements to the right of 4 which is actually smaller than 4, means like 4 with 1 and 4 with 3, you can see this 1 is smaller than 4, 3 is smaller than 4. What is the correct position of this? Actually, in a sorted array, they should be before 4, isn't it? This 1 should lie before 4, this 3 should lie before 4. But here in this particular array, you will find that these 1 and 3 are not in the correct position with respect to 4. Hence, 4, 1 is an inversion, 4 and 3 is also an inversion. Similarly, if you focus on 2 and look on all the elements in the right of 2, you will find that 2 is in inversion with 1, because 1 is actually meant to be on the left of 2, but here it is towards the right of 2. So this is also an inversion. If you consider 3 is not an inversion with anyone, because if this is 3, you look in the right and you have only 5 there, and 5 is greater than 3 and it is supposed to be towards the right of 3 and it is already in the right of 3, so it's fine. Okay, and if you consider 5, it is the last element, so it is okay. So how many inversions did we get? We got 3 inversion, right? So let us understand this again through a code, a brute force technique to solve this particular problem. So as I said, we have elements 2, 4, 1, 3 and 5, right? And we will say that an inversion is detected if any element, if you consider any element and you just look into the right of it, and if you find any element in the right side of this element which is less than this element, then you will find that inversion is present. Why? Because you see, if I am considering this element, I am looking at this element, okay? I am looking at this element 2. And if you parallelly look on all the elements on the right, you will find there is an element 1 which is smaller than 2, which means that in actual, if the array would have been sorted, this 1 would have been present in the right of 2, but here it is in the 1 would have been present in the left of 2, but here it is present in the right of 2, so it is basically not correct position. So this is an inversion. Similarly, if you focus on 4, if you look at 4 and then you just start scanning in the right, you will find that there are 2 elements, 1 and 3. So with respect to 4, 1 should be on the left of 4, 3 should be on the left of 4, but here you can see 1 and 3 are on the right of 4. They are smaller than 4, isn't it? So if they are smaller than 4, in a sorted array they should be in the left of 4, but here they are in the right of 4. So this again, 4 is in an inversion with 1, 4 is also in an inversion with 3. Got the point? Okay, how do we solve it? So let us now understand the brute force technique to solve this particular problem, and then we will move to the optimal solution. So here is my array that I have created basically, and the number of elements in the array. I will be calling the function inversion count, passing the array and the number of inputs or the number of elements in the array as input, as an argument. Now I have received the array and the number of elements in the array. What will I do? I will basically use the value ij, variable ij. Now I will be traversing the the array. So for I equal to 0, I less than n, I plus plus. Got the point? What is happening? I am traversing the array from starting to end. Then for each element, for each value of I, I have to basically focus on all the elements to the right of that element. So for that I will be using a nested array, j equal to I plus 1, and it will also move till the right. j plus plus. What we have to check? So if I show you the working, so basically 2 4 1 3 5, initially I is present here, j will move from here till here, and I am going to count if any element is smaller than this element. So for that I will be checking if array of j is basically smaller than array of I. What does it indicate? It is not in the correct position, sorry. So I'll basically say inversion count plus plus, and I'll be maintaining a variable here, integer inv equal to 0, to maintain the inversion count, right? And finally at the end what will happen? This will give me the total number of inversions present. Return inv. Fine. So that's it. Let's see the brute force technique. What is the issue? Okay, they want a semicolon. And what is my issue? Okay, let me check. Alright. So this is the output. The number of inversions are 3, and this is what we have basically found out initially, isn't it? 3 inversions. Now what are the inversions? The inversions are 2 and 1, because 1 is present in the right of 2. It actually should be in the left of 2. Next, 4 and 1. 1 is present in the right of 4, but actually it should be in the left of 4. And 4 and 3. 3 is present to the right of 4, but actually it should be present in the left of 4. So there are 3 inversions, and the answer is also 3. What is the time complexity of this brute force approach? Now basically, this naive approach basically. So the time complexity of this approach is order of n square. Now how do we say that? Basically you can see there is a nested loop. This runs n times, this loop inside also runs n times in the worst case. So n cross n basically gives you order of n square in time complexity. Space complexity, obviously we have solved this in constant space. So we can see this particular approach basically can solve this particular problem in order n square time complexity and order 1 space complexity. Can we move to an optimal approach? Definitely yes. We have an optimal approach, but then there we have to do a trade-off, right? There are many ways to solve this particular problem, but the approach that we are going to discuss right now, an optimal one, which is better than this, but then there we have to do a trade-off. Now let's see what sort of trade-off is there. So now let us understand the current approach, the new approach, the optimal approach. So as per the optimal approach, what we are going to do is, let me zoom the screen. Okay, so again we will pick up the array 2 4 1 3 and 5. As per the optimal approach, we will be using, or we will be basically exploiting the use of merge sort, right? Basically we are trying to use the merge sort to solve this particular problem. How? You know that in merge sort basically it is a divide and conquer algorithm, right? So it will basically divide the entire arrays into smaller parts. So first of all, what will happen? The mid of this will be 2, so it will divide it into 2 parts. Basically what are the parts? You will have 2 4 and 1, and in the one part you will be having 3 and 5, right? So we will further divide this, isn't it? So this will be divided into 2 and 4, and this will be divided into 3 and 5, right? This will further be divided into 2 and 4. Now see what happens. This was basically the division part, right? Partition part. We are dividing part, right? We are basically dividing this array into equal halves. Now starts the merging part. Now it is at this point of time where we will keep track of the inversion count. For example, if I merge this into a single array, what happens? You see, I is here, j is here, array of I is less than this array of j, so no problem, I'll put 2 here and 4 here, it's okay, right? Now this was 1, let us keep it as it is. Now if you merge these two, right, I was here, j was here, array of I is less than array of j, so no problem, you keep it as it is, right? It will be stored in the new array, 3 and 5, right? I'm not going into depth of merge sort, but I'm just giving you an overview about how things are actually working. This is the merging step. Now what we will do, now you see my I pointer is here, j pointer is here, and array of I is basically nothing but array of I is 2, Got the point? Now we know that this array that we received after merging is a sorted one. This is a sorted array, which means all the elements here are in increasing order. So right now my I pointer is pointing to this element 2 and j is pointing to the element 1, and I found that this element I is greater than this element j. Point to be noted, a of I is greater than a of j. What does it indicate? It indicates that this element is greater than this j, and at the same time this also indicates that all the elements to the right of this is also greater than this. Why? You know, because this array is sorted, means all the elements to the right of this is greater than this, right? So if 1 is greater than 2, then obviously if 2 is greater than 1, then obviously all the elements to the right of 2, that is 4, will also be greater than 1. Now this is an inversion, isn't it? You see, 2 and 1 is an inversion, 4 and 1 is also an inversion, right? So what we will do, we will count the inversion. How do we count the inversion? Inversion count is equal to, basically, we will say the number of elements in this array, suppose the number of elements in this array is n1, minus the index I. So this will basically give you how much? Right now this will give you number of elements in this is 2, the index of this will be 0, right? So 2 minus 0, which will give you 2. So I found 2 inversions at this point. Got the point? Now basically this will be merged into a single array. Things work as usual, right? The merging process will be as usual, just we will keep track of this inversion count. Okay, whenever we find that array of I is greater than array of j. So if we merge it, we will basically have element 1, 2 and 4, right? And here basically we have right now 3 and 5. What next? Now basically you see my I is here, j is here. So if array of I is less than array of j, what happens? You know very well. This is a resultant array. If I is less than j, no problem, you just put inside array of I inside this new array and move the pointer to the next element. Now this is array of I is 2, and here the element is 3. So array of I is once again less than array of j. So any problem? No problem. Just put 2 here and increment the pointer to the next. Array of I is 4 and array of j is 3. Any problem? Yes, we have a problem. What? Whenever array of I is greater than array of j, what happens? I found out that there is an inversion present, right? Isn't it? You see, this element is greater than this element, and we know that actually this 3 should be present in the left of 4, but right now you can see it is in the right of 4, which means this is an inversion. So what we will do? We will increase the inversion count. So 2 plus what happens is n1. What is the number of elements here? Number of elements here is 3. 3 minus what is the value of I? I value here will be 2, isn't it? So 0, 1 and 2. So how much did you get? 2 plus 1, which is equal to 1. Got the point? So we detected how many inversions total? 2 plus 1 equal to 3. Sorry, 3 inversions so far detected, and again this will be merged as usual. 3 will come here, j pointer comes here. Again array of I is less than array of j. True. And if this is smaller, no problem, we will take the smaller pointer and this moves ahead. Right, now only one element left, it will be copied. So 1, 2, 3, 4, 5, the array is sorted. You see, we have basically used merge sort to sort the array, and during the use of merge sort only, we basically maintain the inversion count. Right, now I think it's time to implement the code. Let us quickly jump to the coding part. Alright, so let us now focus on the coding for this particular problem. We will be basically using the merge sort process that we just discussed. So we will just write the entire merge sort problem now. Nothing different, the entire merge sort problem. So I hope you are familiar with merge sort, and please just follow what I'm doing. So this is a long integer inversion count function. Here they are saying that they will be returning long. So basically we are expecting very large values to be returned. So for that particular reason, we will be declaring a variable long result. This will be storing my result, and I will basically be using merge sort. So I am just calling the merge sort function. Merge sort. I'll pass the array. The index of the first element is 0 and the index of the last element is n minus 1. That's it. This is what I'm going to pass here, and this will be returning what? Result. This is the task of this particular function, nothing else, right? So long result equal to, we are just calling the function merge sort, passing the array, first index of the first value, index of the last value, that's it, and the answer whatever will be returned by merge sort will be returned here, right? Return result. That's it. So it's time to, basically we are using merge sort, so basically it's time to use a merge sort function. How do we write the code for that? So let me just erase this. Yeah, so now merge sort it is now, you see, this particular function is basically this particular function here. This function here is receiving what? A long value, which means this function is returning a long value. So merge sort will also be long, right? And merge sort, what will it receive? Basically it has received this long type array ARR. What the point? And what else has it received? It has received the indexes. So I'll be using the index f, suppose, to point to the index of the first element, and integer L to point to the index of the last element. That's it. So this is my function merge sort. What do we do inside the function merge sort? Now since we know that they are going to return a long value, so basically inside the merge sort function we are going to count the number of inversions, as I had said in the discussion right now. So what we are going to do is we are going to declare a variable again, long, let it name count equal to 0. Done. One variable I will be declaring mid. Why? To find out the mid position. So mid position of the array that I have received is equal to nothing but the index of the first element plus index of the last element divided by 2. This is the index mid position of the element array that I have received. What should I do now? So basically 2, 3, 1, 4, 5. The indexes are 0, 1, 2, 3 and 4. So this is my array. What has happened? I have received basically f as 0, L as 4. So mid will be basically pointing to 0 plus 4 by 2, which is 2. This is mid. Now I will be dividing this into two sub-arrays, this one and this one. How do we do so? So I will be calling the merge sort function, merge sort. But when do you think we should divide? We should divide only if you have more than one element. So how we check that? If f less than L. So if f is less than L, only then we will go for division process, because we can divide it. Otherwise, if there is only one element in the array, how will you divide? So merge sort what? Merge sort, I will again pass the array ARR. What will be the first index of this sub array, left sub array? F, right? F. And the last index will be mid. That is why I will be writing array comma f comma mid. Done. That's it. What about this right sub array? Merge sort array comma, what is the first index of the right sub array? The first index of the right sub array is nothing but mid plus 1, right? And last sub array, last index is L. So from mid plus 1 to L, mid plus 1 to L. That's it. And finally we call the merge function. What will merge function do? Merge function will basically combine these two results, right, into a single sorted array. So merge will basically receive the array as argument, the first value, the index of the first element, comma mid, and the value of last. Done. Now remember, we basically have to count the number of inversions, and we know that if we have an element, if we have an array like 2, 3, 1, 4 and 5, what was happening? Basically we were dividing it into 2, 3 and 1 and 4 and 5, right? And this was also further divided into 2 and 3 and 1. This was further divided into 4 and 5. This was further divided into 2, 3. So finally what we had? We had 2, 3, 1 here, 4 here, 5 here, right? So assuming now your array has already been segregated into smaller units. Now it is a time to merge them, right? So you know that whenever I am doing a merge recursive call here, whenever I am doing merge sort, again I am dividing this array into two parts, the left sub arrays and the right sub array, right? So basically I should keep track of the number of inversions encountered here and number of inversions encountered in the right part also. That is why basically I am using the variable count here, and I will say count plus is equal to on the left part also, and count plus value returned by the right sub array also, and also the count while merging them. That's it. And finally when I come out of this, I will be returning what? I will be returning count. Done. This is what I am going to return, the count. Now this was the merge sort function. How to write the merge function? So in order to write the merge function, what do we do? The same as merge sort. So I'll be declaring long again, right? So long merge function, what is it going to receive? a long type array, comma, integer f, integer mid, integer l. Right, this is what we passed. Now what to do? Now basically we calculate the strength of the left subarray, which will be nothing but what is the number of elements in the left subarray? Mid minus f plus 1, right? Mid is pointing here, f is pointing here, so mid minus f plus 1. So we will write here mid minus f plus 1. This is the number of elements in the left subarray. Integer n2 equal to what? Number of elements in the right subarray, which is nothing but l, this is pointing to l, minus the index of this particular element is nothing but mid plus 1 plus 1, which is nothing but l minus mid, right? L minus mid. One more thing, these will store array elements, and we know that the array elements are of type long, so we should also declare this as long, right? Anyway, this is the index, so no problem right now. This is only the count. So now basically we should declare long array A with number of elements n1, and long array B with elements n2. That's it. Declaring some variables I equal to 0, j is equal to 0, k will point to the index of the first element of the left subarray. So f basically, not l, I'm sorry, this will be f. Fine. What to do? Now basically we should run a loop. Now how will the loop work? Basically, first of all I am creating what? A space for the left subarray. I am creating a space for the right subarray. So I am basically storing all the elements in the left, all the elements in the right subarray. Now how we do so? So for that particular reason, I hope you are familiar in the merge sort process. What do we do? For I is equal to 0, I less than length of left subarray, I plus plus, and here what will I do is basically a of I is equal to what? A of I is equal to basically array of f plus I. Done. And similarly for I equal to 0, I less than n2, I plus plus, b of I is equal to what? Equal to array of, now this will basically be nothing but mid plus 1 plus I. So in these two part, basically what we are doing, we are copying the elements to two subarrays, right? The left one and the right one, these two, similar to that one that we do in the merge sort. Now what we should do? Now basically we should start the actual merging process. How we do so? Basically now we will say I is equal to 0, it's fine, j is equal to 0 is also fine. Now while I is less than n1 and j is less than n2, what do we do? While I is less than n1 and j is less than n2, like in this particular process, suppose I am going to merge them. So suppose I am going to, now this is what I have received, right? This is my left subarray, this is my right subarray. Now I is pointing here, j is pointing here. If I is less than n1, true, j is also less than n1, true, and I'll basically check if array of I is less than array of j, right? So what will I do is, if a of I is basically less than b of j, what do? We basically store this smallest element into the array. Array of k plus plus is equal to the smaller element, which is the smaller element a of I. Got it? And I will increase this to next. What? I hope you got the point. So basically I am comparing these two different subarrays. So a of I is less than this, true, so I'll just copy this here 2 and I'll increment the pointer to the next. That's it. Got the point? That is what I have done. Done. Next, if this is not the case, else. Now how will the else part be encountered? You see, so after these two arrays are merged, what will you get? After these two arrays are merged, you will basically get 2 and 3, right? 2 and 3, and here now this is 1. Now it's time to merge these two. Again, this is the left subarray, this is right subarray. I is pointing here, j is pointing here. In this case, you will find that array of I is basically greater than array of j. So basically this condition becomes false. You will move to the else part. Now when array of I is greater than array of j, what happens? You find out that an inversion is present. Why? Because this element 1 actually should be present in the left of 2, but in this array it is present in the right of 2. You see, 2 is on the left, 1 is on the right. So what does it indicate? It indicates this is an inversion. Now how do we count the total inversion in this case? So you see, if 2 is greater than 1, then obviously any element which is after 2, will also be greater than 1, because we know that this array is sorted, because just now we have merged two sorted arrays. So this array is also sorted. Now if this array is sorted, all the elements after 2 is greater than 2, right? So all the elements after 2 means suppose 2, 3, 4 and 5. So if I found 2 greater than 1, now basically 3, 4, 5 will also be greater than 1. That is why how many inversions will exist actually? So total number of inversions I will count here. So I will write count plus is equal to the number of elements in this array n1 minus I. That's it. The number of elements in this array. How many elements are there? 2 elements. What is the index of this element I right now? 0 and 1. 0. So 2 minus 0 is equal to 2. You see 2 inversions are there. How? 2 and 1 is also an inversion, because 1 is on the right of 2 and 3 is greater than 2. So 3 and 1 will also give an inversion, because 1 is also on the right of 3. 2 inversions present. How do we calculate? Length of n1 minus I. Fine. And which element are we going to include here? The smallest element. Smallest element is from this side. So I'll include this element here and I'll increment j++. So basically I'll say what? Array of k++ is equal to b of j, because I'm including from the smaller side, and I'll do j++. That's it. Now what do we do? Now we know that once this merging is complete, there may be some elements which are still left. So for that particular, I'll just copy them. So while I is less than n1, what do we do? Array of k++ is equal to a of I++. Sorry. Yeah, it's true. And while j is less than n2, what do? We say array of k++ is equal to array of, not array, exactly, b of j++. Yeah, fine. And finally, after this, we should return what? The count. Right? Have we declared the variable count? We have not declared. We have to declare the count, right? Because you see we are counting here. So count equal to 0, and it will be typed long. Done. So we are returning the count here, and we already have the merge sort function below. That's it. This should work. Let us see how the problem actually works. So I hope everything is fine. Okay, I'm expecting no issues now. Let us see. Okay, slight error is there. Let me check the error. Okay, actually I'm trying to compile it in C. I should compile it in C++. So let me just change it. Alright, so a very silly mistake. You can see this is an array, right? So I should basically give square brackets here. And also in the other cases also it's fine. One more thing, everything is same. Here basically you can see we should include a condition equal to also, right? Because if it is less than and equal to, then we will just take the element from the left sub array. Now let us compile it. So a single square bracket has actually spoiled our all efforts, right? So please be careful with it. So yes, the code is working fine. Let us submit the code. So yes, the code actually worked fine. So this is the code in front of you. I hope this entire explanation was helpful. In case of any doubt, please feel free to put it out in the comment section, and just like, share and subscribe. Considering the time complexity of this code, so obviously the time complexity is order of n log n, because we are using the merge sort process. Space complexity is again order of n, because it is, you know, using extra space. It is not an in-place sorting. Moreover, in the brute force approach or the naive approach that we discussed, the time complexity was order of n square and space complexity was order of 1. So you see, the previous approach was taking more time but less space. This approach is taking less time but little more space. So basically there is a trade-off, right? If you're trying to improve the time complexity, basically it had to compromise with the space complexity. There are more algorithms, more optimized process to solve this particular problem in order of n also, right? So let's see if I can bring that on board again. So that's all from this video. I hope this video was helpful. In case of any doubt, please feel free to put it out in the comment section. Just like, share and subscribe. Thank you.